If we want to know where an electron is in free space, well, actually, if we want the probability of finding an electron in free space, that's just one. We can always find an electron traveling in free space somewhere because free space is infinitely sized. So if there is an electron there, if we were to just take its wave function, square it, and then take the integral of it, we could find the exact probability of where it is. And if it's in free space and it's infinite space, the probability is going to be 1. So that just means it exists somewhere. We don't know where because the universe is so big, but it means it exists in the universe somewhere, which again is unremarkable. But what happens if we are able to confine the space in which the electron is? And we can do that. There are ways. Again, this is a highly theoretical thing. We can't make the thing that I'm going to trap the electron in. It doesn't exist. It's a theoretical existence. So the theoretical existence is we're going to put the electron in something called an infinite potential well. What that means, it's kind of like it's in a hole, but the hole has infinite sides. So the sides go up and up and up and up infinitely. What are we going to do with that? Well, this is basically what we do. We know the electron's in there because we put it there. So the probability of finding the electron in there is 1. And it can't get out because it would require infinite energy to escape. So in this case, we know that the probability that the electron is inside the well somewhere is 1. And the probability it's outside the well somewhere is 0 because we put it there and it can't get out. The trapped electron inside there has a wave function. It actually has infinite possibilities of what the wave function could be. The only parameter that has to be followed within this well is the wave function has to equal 0 at x equals 0, and it has to equal 0 at x equals a. And there's an infinite number of waves that can happen that way. They're standing waves. They're not traveling waves because it can't go anywhere because it's inside an infinite potential well. But there are different energy levels, and at each energy level, there's just a standing wave. And each time you go up in energy, it just gets more lobes. And that's what they kind of look like. I mean, it doesn't really. But the electron can exist in any one of these standing waves inside that infinite potential well. Can't get out, but depending on how much energy it has, it could be anywhere in those discrete energy levels. Now we can figure out the energy of the electrons in there because we already have an equation that does that. This is slightly different than the one we used before, but because it's in a potential well, we can find the energy. Remember, h bar squared is a constant, pi is a constant, 2 is a constant, m is a constant, and the only things that are not constant is n and a. A is the width of the well, and n is the quantum number that goes up the side. So there's only 2 numbers that are variable. Everything else is a constant. So we can figure out the energy levels that these standing waves exist at. We can figure out a width A, and in this case it's 5 angstroms. And we can figure out then the different energy levels for n equals 1, 2, 3, and 4. Not too difficult. We do have to change this to electron volts because most of the energies are in electron volts. So if we plug in A, because we know what that value is, and we take the 6.018 times 10 to the minus 38, and we divide by 5 times 10 to the minus 10, we get the answer in joules, and then we have to divide by 1.6 times 10 to the minus 19 to convert it to electron volts. So it's just n squared times 1.51 electron volts. So the first energy level is 1.51 electron volts. The second one, we would multiply that by 4, because that's 2 squared. We'd multiply it by 9 to get number 3, and we would multiply it by 16 to get number 4. So we've got several different energy levels, and then we can go back to that original infinite potential well and put the energy levels in next to it. So we can just put those in. And the electron can basically exist in any one of these states inside this well. It can be a one-lobed standing wave with 1.51 electron volts of energy, or it could be the higher frequency wave up at the top with more energy. You notice that as the energy goes up, the frequency of the wave goes up because there's more energy. The probability of each one of those waves is just related to the square of the absolute value. So we could actually kind of figure out by taking the square, it changes the shape, and then take the area underneath. We could figure out that value if we wanted to, but we're not going to because we really don't need to. So we've established the fact that an electron in an infinite potential well that can't get out has different standing wave patterns with different energies. So, let's say we have a stream of electrons, and now they're traveling towards a well that has a finite height, but infinite width. So the value of A is infinity, but there actually is an energy level that could be attained to get in. Well, the problem is, if the energy is greater than V naught. V naught is just the potential energy that's needed to get over it. If the energy level is greater, the electron's just going to pass right over it and never go in. Makes sense? If the energy level is less, they're going to get to the side and they're going to bounce and they're going to go back. And that's what you expect. So, what you expect is that no electrons would ever get inside. But they do. They actually do get inside sometimes. Again, this is why electrons are unpredictable. What ends up happening is some electrons go through and they bounce around all inside, and then they come back out and they do get reflected, and they get reflected exactly the same spot where they were supposed to end up. But they take a detour and they go inside the well and they go all inside and then they come back out. And you don't expect that. You expect them not to be able to get in there, but yet they do. We can change this even further, and we can get a well that has finite height and width. So now there's like an A value, an x equals 0 and an x equals A. But what this means is, since some electrons can get inside, some electrons could probably get out the other side and go all the way through. Not very many, but some. So there is a finite probability that some electron might be able to go through here and might be able to come out the other side. Even though it shouldn't be able to, it may. And the wave function actually changes when you do that. It's kind of bigger, and then it goes down through this kind of well, and then it comes out and it has a different frequency. But the whole point of this is that electrons travel to places we don't expect them to be able to. So we can't say where they are exactly, and we can't say necessarily where they're going to go. Yes?
So whenever that box had a finite size, did it still have infinite potential to enter the box?
No, it had a finite energy to enter and a finite energy to exit, but these are electrons with less than that energy. So they should not be able to enter or exit, and yet they can. So in this class, we mostly talk about electrons and where they are and where they're going, and we spend a lot of time talking about that. And they do some really weird thing. And this whole thing that I just described is called tunneling. It's basically going through a barrier that they're not supposed to be able to go through, but they can. And there are actually devices that are based on this, like a tunnel diode. It's actually based on the fact that electrons will do that. And they'll predictably do that, which is weird because they shouldn't predictably be able to do something that they're not predicted to do, but they can.